These are some actual signals. Oh, if my brain worked a little bit better, there we go. If a machine was doing this, we wouldn't have a problem. The bottom signal, this is the EMG, muscular signal, showing the tremors. If this particular sequence, just to show you what's going on, 45 to 50 seconds, everything's all right, and then the tremors start up. So this is an indication that the tremors have started. The sequence above is the signals picked up at the same time. This is an actual patient, the same time in the patient in the subthalamic nucleus. And I think if you look at that, you can see around the 45 to 50 second mark that the variation of the signal changes a bit, we can see. Now, it turns out that in some patients, the variation of the signal diminishes, and in other patients, it actually increases. I mean, we're trying to understand what are their differences. Are there different types of Parkinson's disease? It may be the positioning of the electrodes. There's all sorts of reasons. But whatever, what we've done, just to show you what's possible, is to train a neural network, an artificial neural network, to recognize, first of all, when there are tremors, but then to predict when there are going to be tremors. We see the output, if anybody knows about this, it's a multi-layer perceptron. It's a fairly standard artificial intelligence procedure. At the 45 to 50 second mark, the output goes high. This is simply flagging that the tremors have started up. Great, fine, but it's showing it's recognized them. Around the 14, 15 to 19 second, we get some spikes. The network is saying something's going on. And in fact, if we look at the EMG signal, and maybe even the electrical signal, the local field potentials, it's as though the tremors start to get going, but they don't get going. Something happened, but it doesn't kick in. But the network has picked it up. Most important of all is this thing here, the 30-second point. There's a big spike. Something's going to happen, or something's not happening, so there must be something going to happen. And sure enough, 15 to 20 seconds later, it kicks in and off it goes. Now, we've got data now, this type of stuff, on over 200 patients, and are able to train neural networks pretty reliably to carry out the same sort of prediction. This 15 to 20 seconds is perhaps at the longer end. Some of them it's about 10 seconds, but the networks are pretty clearly able to pick up something is going to happen in about 10, 20 seconds time. So what we're doing now with the surgeons is to look to apply an actual feedback loop. So to have the stimulator not working, but only working when the network says, okay, kick in, to stop the tremors, and then off we go until the tremors are predicted again, hopefully with a view to reduce the amount of power requirements. I think one side effect of this work is not just the predictor, but the fact that something is going on deep in the patient's brain that an artificial intelligence system can pick up and predict what is going to happen in the human brain before it actually happens. 15 to 20 seconds is quite some time. I mean, you can go and have maybe a cup of coffee, I don't know. I mean, maybe it's not enough time for sex and things like that. With my first wife, it'd be far too long. But it's a long time, and you can use that to predict. It's plenty of time to apply a stimulation or to give the person an indication something's going to happen and so on. Now, as you know, the same stimulator is used in different parts of the brain for a much smaller number of people for epilepsy. And what we're doing now also is looking at the data for patients with epilepsy and seeing if we can come up with the same sort of predictions. It looks as though it will be possible. Of course, the same stimulator is used in more research cases for people with Tourette syndrome and also even clinical depression. And so there are potential, all sorts of strange applications if we can predict what's going to happen. So if you can imagine now, if we could predict that somebody is going to feel depressed, so with their stimulator, it only switches on when they're going to be depressed, clearly they would be there, fine, 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 and suddenly they feel, oh, isn't life wonderful? And then they start worrying about the fact they were going to be depressed, and then what am I going to, isn't that what, so you get into strange loops. Clearly, there are all sorts of ethical questions for using it outside the Parkinson disease, perhaps epilepsy area. But even if you look at epilepsy, the possibility of a prediction in a reasonably accurate, I mean, it doesn't matter if it predicts occasionally that there is going to be a fit or there is going to be a tremor and it didn't get it right. It doesn't matter about that because it's still better than the system. If it gets it wrong and it doesn't predict, then that's not so good. So you don't mind false predictions, false positives, as it were, as long as they're not too frequent. The last of the experiments is the one I've been mostly involved with myself. Some of you may know about it, but let me fill you in. Reasons for it. And this crosses the boundary of therapy and enhancement. This is Campbell Aird, who lost his arm due to cancer. He's been given this articulated arm, but you see he's actually controlling it with his hand here. You'll see him flicking a switch, and many of the methods for bionic arms use other parts of the body to operate it. I mean, to me it seems a bit silly that he's having to use his left hand to control his right hand. I think the best that I've seen, Todd Kuiken's work up at Chicago, the Rehab Institute, where he's grafted on nerve fibers to muscles, but then they need electrodes on the outside of the muscles, and that limits the amount of time people can use it, but nevertheless it's excellent work. But it would be much better, surely, if we just had a straight interface from the person's brain, and we had presentations yesterday looking at that, or nervous system, onto the wires. This is where it gets fun, though, because if we started, what I would look at, brain signals, neural signals if you like, not just being in the brain or nervous system, but appearing on the wires of the arm, then from a technological point of view, we can clip on those wires, we can send those signals wherever we want. They don't have to stay within the body. So if we're able to have a bidirectional interface from the brain to technology, then okay, we can look at rehabilitation, we can look at therapy, but whoa, it opens up all sorts of possible enhancement. Your brain, if you plug yourself in, if you like, can start controlling, not just controlling your body, but it can start controlling, well, wherever the internet takes you. You can start controlling a vehicle on another planet. You don't have to send astronauts to Mars or wherever you want. You can stay at home and just send a connection to your nervous system up there, and it'd be like you're there. And also you can sense things on another planet. You can sense, not just limiting to infrared, to human senses. You can go to infrared and ultrasonic. You can extend your sensory range. So if you're able to plug yourself in, then you can extend your capabilities wherever you want them to be. This is me lying on the operating theatre in the Radcliffe Infirmary in Oxford. Team of 4 neurosurgeons. What they did, some of you may recognise this. Now it's called the BrainGate system. It used to be called the Utah Array. 100 electrodes, 1.5 millimetres long. The spikes, the electrodes themselves, are 1 to 3 micrometers, that sort of size. So the electrodes are around the neuron size. And 100 of them, and this was fired into the median nerve fibers of my left arm. Here's highlights from the we haven't seen much blood so far, so here's the highlights of the operation. What you see there, this is my arm. What they had to do was to make 2 incisions, but sort of make a tunnel to start with a metal rod, and then put this tube down so that the 100 electrodes, they could feed down the tube. They then moved the tube out of the way, leaving the electrodes in position. On my nerve fibers, they removed some of the myelin sheath, put those 100 electrodes on, hammered it into place, and sewed it all up. So I had for the 3 months, just over 3 months that this was in place for the experiment, this was like an external connection from my nervous system, which we could simply plug in here, plug into the computer, or I had a little fancy radio transmitter receiver unit so we could have a bidirectional, and this was a bidirectional link, I should say. not just monitoring the signals on my nerve fibers, but we were able to stimulate my nervous system, which was important. Now, I've got a little clip from Discovery TV. Sorry it's a bit funky, but give you some idea of some of the things I was able to do.
With technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralyzed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. There we go, the singularity, of course. Oh, thanks very much, thank you. Yeah. I didn't want to mention singularity in the clip. Ray sells enough books anyway. So, just a few holiday snaps to conclude with. This is wearing a baseball cap with ultrasonic sensors on it. The output from the ultrasonic sensors was fed down onto my nervous system. What was happening when an object came closer, my brain was receiving pulses of electrical current that we were feeding in, stimulating my nervous system, which my brain took us 6 weeks to train my brain to recognize the pulses. As an object came close, the frequency of the pulses increased. As an object moved further away, the frequency was reduced. So I was able, with a blindfold on, I could move around and detect objects very reliably. I didn't know what they were, of course, but I could recognize where they were. And it does give you ultrasonic input. If anybody's not had an extra sense, one or two of you may not have had, it does give you ultrasonics, quite a reliable sense of distance, which we're not really all that good on as humans. Here, Ian, my researcher, when he brought the board further away from me, brought it closer to me, I was trying to follow ultrasonically to stay the distance away from it. This is my wife, Irena, again, wearing a piece of jewellery a student at the Royal College of Art put together. I think you guys, forget flowers and things for your wife. This is what you have to do. This was linked to my nervous system. And you have all sorts of ways. It could be just open, close my hand, so neurally controlling my wife's jewellery colour. It changed from red to blue. But on the nervous system, it's pretty easy to detect different signals. I think Ros Pickard at MIT is picking up signals to do with anger, stress in drivers. Clearly, when you're calm or when you're excited, you can pick up quite clearly the frequency of the signals on the nervous system. So if you imagine here, when I was calm, my wife's jewellery was blue, and when I got excited, her jewellery started flashing red. She works in a different place to me. So if you can picture her there with her blue jewellery, starting with blue to start with, fine, he's not doing anything he shouldn't. Suddenly it starts flashing red. What is he doing? And who is he doing it with? So I don't know whether that's such a good idea. This is me. The guys at Columbia University, the real-time computing labs, helped us out. This is me in their labs there in New York. What we did was to plug my nervous system into the internet. It actually had an IP address. So if you'd have known, you would have been able to send signals directly onto my nervous system. The security was we didn't tell people what we were doing. What we did was link up to the robot hand that you saw before, the one with Campbell Aird, the same hand, back in the labs in Reading. So when I moved my hand in New York, my neural signals were sent across the internet to move the robot hand in Reading. And it mimicked, there was a slight time delay, but it mimicked the hand movements pretty well. The hand has, the robot hand that is, has fingertip sensors on it, and signals from those sensors were sent back across the internet to stimulate my brain in the same sort of way. So as it gripped harder and harder, the frequency of signals increased. And what I was trying to do without looking at it was to get the fingertips to just to touch an object, so not to, so that the signals almost died away, but not quite. And again, that worked very well. All sorts of questions, of course, in terms of the hand's mechanical design and so on, but we were looking more at the neural control of the hand. So it'd be quite possible from a neural control point of view for an amputee to have an artificial hand with a suitable interface that is reliable and durable, which again was not part of the thing, but to control a hand from a neural point of view. The final part of the experiment, which I did talk about in the discovery clip, what my wife had, you can try this tonight if you want. She had what's called microneurography. I'm sure most of you know about that. It just involves putting wires into your nervous system. So if you try tonight, just push some very thin wires into your nervous system. You will find it is extremely painful. And we thought she was going to have some anesthetic, but the doctor said, no, I need to make sure I've made a good contact here. So he pushed the electrode, and she screamed, and he said, yeah, I think we've made a good contact there. He pushed another electrode in the same way, another wire, and we went back to the lab and electrically linked our nervous systems together. So what happened when Irena, my wife, when she moved her hand like that, my brain received a pulse. And when she went ding, 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 my brain said ding, 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 3 pulses. So what we did was communicate in a very basic way, telegraphically, in fact, radio telegraphically, a sort of a very simple Morse code, if you like. But it was just proving the point that you could do it. We were doing, I mean, I guess there was an electrical connection directly from brain to brain, if you count the nervous system as part of that. And if I move my hand, her nervous system receives signals in return. So it's a very, very simple form of communication, which when we're looking to brain computer interfaces, which I know there's people talking later today and the presentations yesterday morning, I found it very, very exciting as the possibilities that are there. Disappointed to hear it's going to be animal trials first, because I'm eager to get hold of it myself. Because quite clearly the step from this is to go from nervous system to brain communication. And that's definitely what I would like to do in my lifetime. I've got a few years, so hurry up with the research. Hopefully, therefore, I would say within a decade, if the technology is there, we can be communicating directly from brain to brain in a very basic way at first, but I mean, one of the reasons for doing this is looking at how poor humans are at communication now. We take complex signals and we translate them into this stupid coded mechanical pressure wave, and then our ears, or somebody else's ears, convert the signals back. And we, of course, when you've been married for 40, 50 years, your wife still has no idea what you're talking about. Whereas if you could send signals directly between brains, it opens up all the possibilities. Colors, images, graphics, we have an idea. You can actually get ideas across to students. I mean, believe it or not. The possibilities of communicating in a much more effective, much more efficient way are enormous, and therefore carrying out experimentation in that area excites me enormously. Now, I know that you do have a little bit in that country down south from here called the United States, a famous politician who used to be a cyborg in the science fiction world. And I would like, if I may, just to conclude with a few of his profound words, named Arnold Schwarzenegger, for those that don't know. And that is that I have been a cyborg, part human, part machine in the past. And as far as being a cyborg is concerned in the future, I'll be back. Thank you.